are going to learn about the difference between B trees and LSM trees. So when to use B trees and when to use LSM trees, and in which application, in which condition. So please make sure that you have watched previous videos explaining B trees and LSM trees in detail. And it is essential to understand the differences in how each data structures handles operations, storage, and performance. The choice of data structure depends on the factors such as write heavy or read heavy workloads, storage efficiency, and system requirements. So let's talk about the write performance. LSM trees tend to perform better for writes due to their sequential write pattern, while B trees can experience higher write amplification because of frequent page splits. So let's take example of write performance in B trees. In the traditional relational database such as MySQL or PostgreSQL, when inserting the data or updating the rows, B trees are used for indexing. If the page in the B tree becomes full, due to multiple inserts, the tree needs to split the page into two, which involves additional disk writes. And this is known as write amplification, which can slow down the process of inserting data. So if you are not able to visualize this, then go and check out the previous two videos, because that will help you to understand the differences in better way. Now let's talk about the write performance into the LSM tree. So in Apache Cassandra or HBase, both of which they use LSM trees. So new writes are first inserted into the MemTable. Okay, let me open the diagram and talk about. Okay, so here you can see the new writes are first inserted into this MemTable, which is in the memory. And once this MemTable is full, data is written into this disk in the form of SST tables. This process involves writing the data sequentially, making it faster for SSDs or HDDs. And over time, compaction processes merge these SS tables to reduce fragmentation and optimize storage. So, what is our conclusion? LSM trees outperform B trees for write heavy applications such as log storage or time series database. Okay, so let's talk about the read performance. B trees are generally faster for the reads due to the structure of the tree, which allows the direct access of the data. While LSM trees can be slower because data might be spread across multiple SS tables. So let's understand by taking the example. In a financial application which is using the MySQL for transaction logs, each transaction might be indexed by a B tree. And when retrieving the specific transaction, the database performs the quick search through the balance tree. Since every key is in exactly one place, reads are very predictable and efficient. So let's talk about the read performance for LSM trees. In Apache Cassandra, when querying the data, it might involve checking multiple SS tables in various stages of compaction. If you query a key that has been updated multiple times, you have to check several SS tables, and which can lead to slower reads as compared to B trees. However, Cassandra mitigates this by keeping the MemTable in the memory. But still, complex queries might need to merge results from multiple data structures. So here the conclusion is B trees are more suitable for the applications which is requiring low latency reads, such as e-commerce sites, because they have to quickly retrieve the product details. LSM trees work better for the eventual consistency models where the read speed is the low concern. Okay, now let's talk about the storage efficiency. LSM trees provide the better storage efficiency because of the compaction, while B trees may leave unused spaces due to fragmentation. Now let's understand by taking an example. So in B trees, for example, while using the PostgreSQL, when data is updated, the old data can become the fragmented, especially if the row grows larger. After multiple updates, unused space may accumulate in the B tree nodes. Over time, this wasted space results in the database using more disk space than necessary, which can be problematic for the large scale system. So let's talk about the storage efficiency in level DB, which is using the LSM tree. As data is returned to the disk, compaction runs in the background to merge the SS tables into larger ones, eliminating fragmentation. This process allows smaller disk usage as unused space in old SS tables is reclaimed during compaction. Furthermore, compaction techniques such as Snappy can be applied to SS tables to reduce the disk usage. So, conclusion is LSM trees are more storage efficient in cases where data is frequently updated or deleted, as seen in NoSQL databases used for log aggregation. Okay, so let's talk about the write amplification. Write amplification refers to the additional writes required beyond the initial data write. B trees and LSM trees both experience write amplification, but LSM trees handles it differently. For example, let's talk about the write amplification in B trees. Consider a scenario where you are updating a record in a B tree based database like SQLite. If the updated data doesn't fit into the existing data page, the page is split, requiring multiple writes to the disk, one to the log and another to the updated page. Over time, multiple updates to the same key will result into the multiple writes to the disk. Let's take an example of LSM trees and write amplification. In Apache Cassandra, when a key is updated multiple times, it may exist in several SS tables until the next compaction operation occurs. During compaction, old versions of the data are discarded, but multiple copies of the same key can exist temporarily. The compaction process can cause write amplification because older SS tables are rewritten even if only a small portion of the data is changed. So the conclusion is LSM trees tend to write less frequently to disk in high write workloads, but the compaction process can cause temporary write amplification, especially when a large amount of data is being updated. B trees may be better in the scenarios predictable write patterns like transactional systems. So let's talk about the compaction overhead. LSM trees face compaction overheads that can affect performance, especially in the systems with high write throughput. So let's talk about the compaction in the B trees. B tree based systems don't require compaction since the data is stored into the well organized structure. Updates or deletes are applied directly to the tree and page splits are handled as needed. There is no need to periodically rewrite the data in the tree, making the overhead predictable. So let's talk about the compaction in the LSM trees. In Cassandra or RocksDB, compaction can become the performance bottleneck during the periods of high write throughput. For example, if the database is receiving the high volume of updates and the compaction process can't keep up, it might lead to increased usage and slower reads. This is especially problematic when the system has large amounts of data and compaction cannot efficiently reclaim the space. So the conclusion is B trees avoid the complexity of the compaction but still incur some overhead with page splits. LSM trees are more efficient in terms of storage but can have performance degradation if compaction is not managed properly. Okay, so let's talk about the transactional semantics. B trees provide the strong transactional semantics because each key is stored in exactly one place, making the transaction isolation easier to implement. LSM trees, on the other hand, requires more effort to ensure strong isolation due to the multiple copies of data. So let's understand transactional semantics in B trees. In a banking application using the PostgreSQL, which is using the B trees, transactions are implemented with the ACID properties. If the customer transfers the money, the database uses the locks on ranges of the keys to ensure isolation. And since B-tree stores each key into one place, locks can be applied directly to the index, guaranteeing consistent transaction processing. So let's talk about the transactional semantics into LSM trees. In Cassandra, ensuring strong consistency in a distributed environment can be challenging because single tree might be appearing in multiple SS tables. Managing concurrent updates and ensuring the transactions are isolated is more complex. Cassandra uses the lightweight transaction mechanism based on quorum reads or writes, but it does not provide the same level of isolation as relational databases with B-tree index. So the conclusion is B-trees are a better fit for transactional system where acid compliance and isolation are crucial. LSM trees are more appropriate for distributed database with eventual consistency but may require more complex mechanism for ensuring transaction isolation. Okay, so we have discussed all 6 points, but let's understand when to use B trees or LSM trees. B trees are best for read heavy workloads like e-commerce websites such as Amazon, Flipkart, where quick lookups are crucial. It is ideal for transactional consistency and system requiring ACID properties. Transactional consistency. It is suitable for relational database or file system structured systems. So LSM trees are used for write heavy workloads such as log aggregation systems or time series databases where high throughput is necessary. It is ideal for distributed systems that prioritize high write throughput and space efficiency. And it is useful in NoSQL databases such as Cassandra, LevelDB, or HBase. So this was all about LSM. If you like this video or have any suggestion, then please comment down. And if you want me to make video on any particular topic, then also you can comment down the topic. Make sure you are subscribing to the channel because it will motivate me to make more videos. Share with your friends because in this series we are making the concepts of system design very easy. So after watching this series, you can start reading Designing Data Intensive Applications book. Thank you so much for watching.